Alright guys, so another conic section here, the hyperbola, basically looks kind of like two parabolas, even though they're not technically parabolas, but there's like two branches, the red branches, and they each have a focal point, or there's two foci here, and the definition geometrically is basically this. If you take any point on the hyperbola, let's say there's a point right here, okay, if you measure the distance to one focal point, let's say that's D1, and then that same point to the other focal point. Okay, what ends up happening is the difference in those two, whatever D1 minus D2 is, it's going to stay constant no matter where you go. So for example, if I have a different point on the hyperbola, let's say I'm over here, okay, and I take, let me call that D3, and the distance to the other focus is D4, whatever that difference is, it's going to be the same as the difference of D1 minus D2. So basically the definition is going to be, for the hyperbola, the set of all points for which the difference of the distances from 2 points is constant. Okay, so that's just kind of what makes it shaped the way that it is. If you remember, for the ellipse, it was more like the sum of those distances remains constant, so this one's more about the difference. And you'll notice actually in the equation, where an ellipse would have a plus in between the terms, the hyperbola actually has a minus in the two. Okay, but anyways, let's take a look at a couple examples, how to graph them, some of the properties, how do we find these foci, all that good stuff. Okay, let's take a look. The two branches. Alright, so here's an example. We want to go ahead and sketch the graph and then identify the vertices and foci. First off, the general form of these things, what they should look like. Let's put a page in there first. Is a sample, and let's talk about how to graph these things. And my advice really is to honestly think of these at first very much like an ellipse. Okay, think about the center the same way you would have the center of an ellipse. So for this one, looking at the numerators, that x doesn't have anything with it. The y, I see a minus 1 squared, so we're still doing opposite. So the center of this is going to be 0, 1. Okay, and then actually do the same kind of thing you would do for an ellipse to get the stretching. Okay, and then from there we'll adjust things a little bit. But for example, for this one, underneath the y is a 9, right? So that means that is the a squared term. So the a is just going to be 3. So we're going to go up and down 3. Okay, and put little dots there. Okay, in the x direction, there's a 25 underneath, so that's 5 units, right and left. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay. Now, if this was an ellipse, right, if there was a plus in that equation right there, we would just draw the ellipse and our graph would be done and we could find the foci and all that good stuff. But this one is a minus. Okay, so what we're going to do to change this up a little bit, we are actually going to draw a box using these, and this is just going to help make the figure a little easier. This box now is not really like part of the hyperbola, but it helps make the shape correct. Okay, because with these hyperbolas, remember they're going to have the two, let me go back, asymptotes are going to be the diagonals of that box that we just drew. So it's going to go from corner to corner through the center, so just kind of eyeball it. You know, these don't have to be perfect. But one would go like that, one would go like that. Okay, and that's just setting up the asymptotes, and again, our graph is just going to approach those. It's never going to quite reach them, but it will definitely get closer. That's what asymptotes generally do. And now all we need to do to draw the graph, okay, since it's the y term first, we're going to have our vertices up here and down here, and we're just going to try to keep the parabola branches somehow within the asymptotes. These are really difficult to graph super accurately, so I'm not going to be like, you know, most people aren't going to be checking your points or whatever for super accuracy, but make sure they open the right direction, make sure they stay within the asymptotes and all that good stuff. Okay, so that purple graph, that is the hyperbola. Okay, so that means for us, the vertices, okay, since we were opening up and down, the vertices are going to be the top and bottom point. So it looks like for the top, the coordinates would be 0, 4, and the denominator would be 0, -2. Okay, so that's our vertices. Now the foci, okay, foci are slightly different than they were for an ellipse. The foci on these, okay, let me go back to F. than where the vertex is. So it might be out here and down here or something, okay? So we're going to find that distance, okay? But the reason I'm mentioning it, that they're farther away, the distance from the center to the foci is still c, okay? But now c squared is actually the bigger, it's bigger than a, right? A is only the distance, in this case, a squared was 9. A was only 3, okay? The value to c, since the foci are farther away, is going to be bigger than that. So the equation is going to be like, it's going to look more like the traditional Pythagorean theorem. It'll be the c squared equals a squared plus b squared. Because in this case, again, c is the biggest of the 3. Okay? With hyperbolas 2, the a squared is always the one written first. It's not the bigger one like it is with an ellipse, because remember, the term that's written first is kind of determining where the vertices are and which way the graph's open. Okay, so a squared is 9, the b squared is the other denominator. Okay, so our c squared needs to equal 9 plus 25, so 34. That means c would equal the square root of 34. Okay, so that's telling me, so let's think of the square root of 34 as just a little bit less than 6. Okay, so the coordinates of the foci, okay, are going to be from the center now. They're up and down. They're above and below the center. So we will be adding and subtracting from the y value of the center the square root of 34. Okay, that'll give you those. So the way I drew them, they would actually be a little farther out. 1, 2, 3, 4, 5. They'd actually be maybe up there. And 1, 2, 3, 4, 5, almost down there, okay, to get an approximate location. Okay, so that's that. That's how you graph a hyperbola. Let's take a look at another example. All right, so example 2, one of these ugly ones, right? It's not in the right form. So we're going to have to do some work. All right, let's do some completing the square, one of my favorites. All right, so let's take this equation. Let's do some work on it, see what we can do. I'm going to rewrite it over here. And just kind of rearrange the terms like we normally do. Now, here's one thing to point out. Okay, notice on this one, there are x squared terms and there are y squared terms. Okay, but one of them's positive and one of them's negative. That's your hint, okay, that this thing is a hyperbola, because that has the one with the minus in between. Okay, different signs. We're going to do everything pretty much the same way, though. Okay, so let's rewrite this. So we have the 9x squared. I'm just going to write the x term next, plus 18x. Then we have the minus 16y squared, minus 64y. And I'm going to also add the 199 to the other side there, so that we can start getting this in the right form. Okay, here's where we're going to complete the square each. So I'm looking at the x terms first. Factor that 9 out. Become x squared plus 2x. And we'll complete the square. So based on the value of 2 in the middle, we always cut it in half and then square that. So half is 1 and 1 squared is 1. Okay, with the y terms now, we'll factor out, we do have a minus sign, so factor out the 16. We'll get y squared. Now we divided out, we factored out a negative 16, so that minus 64 is actually going to become a plus 4y. And we'll complete the square too. Okay, and let's move this a little bit. And we're going to complete the square based on the plus 4. All right, so half of that is 2. 2 squared is 4. Okay, now we still have the 199 sitting here. We do need to balance out what we just added. Okay, so we added 2 things. Okay, the first one with the x's there, we added a plus 1, but it was multiplied by 9. So we really need to do a plus 9. And then with the purple, the y terms, we added a plus 4. It was really times negative 16. So that was really like going to be a minus 64 that we need to balance out. Okay, so what we've done, what we hopefully have done correctly, is created perfect square trinomials here. Okay, that one and that one. By completing the square, our goal was to get these perfect square trinomials. So we have the 9 there. The x squared plus 2x plus 1 is really x plus 1 squared. We have the minus 16. The next one, the y squared plus 4y plus 4, is really y plus 2 squared. And then combining all these terms, 199 plus 9, take away 64 is 144. Okay? So very similar to the ellipse, we need that to be a 1, so we're going to divide every term by 144. Okay, and we're going to do some reducing. Okay, we're looking at 9 over 144, and then also 16 over 144. So those both are reducible. The 9 over 144 should become 1 over 16. And the 16 over 144 should become 1 over 9. Okay, and this side, of course, is 1. All right, so we got it in the right form. Let's see if we can go ahead and graph and find the foci and all that good stuff. So to graph, again, we're going to plot the center. My center here is going to be, based on those numerators, -1, -2. So down here, and in the process, this weird process, we're gonna use the box to set up where the asymptotes are, right? So we're gonna look at the denominators. Okay, taking a look at those denominators in the x direction, it's 16. So I'm gonna go 4 units left and right from that center. 1, 2, 3, 4. 1, 2, 3, 4. And in the y direction, there's a 9 underneath, so 3 up and down. 1, 2, 3. 1, 2, 3, and that's going to give us our little rectangular box to set up the asymptotes. Okay, asymptotes will go through the diagonals and through the center. Okay, and we do want to see these on the graph. It really just helps get a little bit of the accuracy. But then as far as our final answer, we now just need to know which direction this one opens up. So since the x term comes first, right? The x term is the first one. That means it's going to be opening on the left and right sides. Okay, that's what determines whether it's top and bottom or left and right. Okay, so the vertices on this one were those two right and left side of the rectangle. So it looks like we're at 3, -2, and also -5, -2. Okay, and that is the coordinates of the vertices, because it's plural. So if you remember what an ellipse was like, this is going to be very similar. We could have x minus h squared over a squared. Instead of a plus, though, we'll have a minus. Y minus k squared over b squared. And it does still equal 1. Okay, so it could look like that. Or we could have the y term written first, y minus k squared, and then the x term. Because remember, when you have subtraction, the order that you write them in matters, right? Like with the ellipses, it doesn't matter if you write the x term first or the y term first, because they're getting added together either way. In this case, since it is subtraction, it does matter. And honestly, a quick little sketch of what the difference will be. Whichever term is written first is going to determine which way those little branches open. So this top one would have branches opening to the left and right, because that's the x direction. Okay, but if the y term is written first, the two branches are going to open up and down. Okay, so you're always going to have 2 branches. It's going to be one of these 2 options. And again, that's determined by which term is written first. Is it the x term, left and right, or is it the y term, up and down? And then we're still going to use the a squareds and b squareds to help us find the focal distance, which is still c squared. So let's take a look at how that works. Back here to that page, the one we're doing right now is going to look like this. Okay, and they actually have asymptotes. Okay, and that's what that box is going to help us. So this page, the foci are always going to be a little bit inside of the curves. Okay, so they're going to be farther away from the. All right. Okay, oops, let me go behind. Okay, or help us. Another couple examples. Is that it? Yes. All right. So let's take a look here. Can we use the information provided to write the standard form? So if they give you a graph, okay, let's see what the graph is. Can we write the equation of this hyperbola? So we should be able to see the center. Okay, they gave us those asymptotes. It was kind of nice. So the center is right there, and you can even see the outline of the rectangle that they use, the box there, right? Okay, that's going to help us write this equation. So if we take a look, we think about the center, okay? We also need to think about while we're doing this, here are the vertices, right? Because this graph opens right and left. So that's important. I need to write the x term first, okay? Because it's opening to the right and left. So I know this needs to be, if our center is sitting at, what is that at, 1, -2, I know we need to do the opposites in here. So x minus 1 squared over something minus y plus, right, 2 squared over something equals 1. And then to find those denominators, let's look at how far this rectangle got stretched out, right? In the x direction, it was 1, 2, 3, 4 left and right, so 16 under there. And 1, 2, 3 in the y direction, so 9 under there. Okay, so that would be the equation, kind of working backwards. I find that very helpful. If you can take a graph, get the equation, it helps you understand how to graph it too. Okay, all right, and let's do one more. Sometimes they can give you like pieces of the puzzle, right? They'll give us a number 4 here. They're going to give us vertices and foci. So let's maybe get a quick sketch, see where things are at, and see if we can come up with the equation. All right, so this one we have coordinates of vertices and foci. So let's sketch what we got, just kind of a rough idea here, and see if we can piece everything together. So my vertices are at 6, 6, and then also 6, -8. Okay, so I'm just going to eyeball where that might be. 6, 6 could be there. 6, -8, somewhere down there. Okay, so those are the vertices. That's key. If the vertices are on the top and bottom, that means the the hyperbola must open up and down, right? It always goes through the vertices. Now the foci are going to tell us, well, not going to tell us, they're going to help us find the values for the denominators of this guy, okay? First off, though, we can find the center right now. If you know the vertices, you know the center will be right in between the two. So I'm looking at the y values go from 6 to -8. So the midpoint of 6 and -8, right? 6 plus -8 is -2. Divided by 2 is -1. So that tells me the center needs to be at 6 and -1. So right about here is our center. Right, and we can verify that that's 7 units away from the top vertex and 7 units away from the bottom vertex. Okay, that's also going to be useful information for us. That distance from the center to the vertex being 7 means that that's our value for A. Okay, the other key piece of information, look at the coordinates of the foci. Okay, the coordinates of the foci, we see there's the vertex, 6, -1, but then it's plus and minus the square root of 130. So plus and minus a little bit more than 11-ish. Okay, but what that's telling me, that 130, the square root of 130, that's the distance from the center to the focal point. Okay, the focal point might be up here somewhere and down here somewhere, but that value of, from the center again, see the y-coordinate of the center is -1. Adding and subtracting 130 tells me that our value for C, let me try and highlight on here, from the center to there, right, the value of C is the square root of 130, okay, because that's how far it is to the focus. So we know A equals 7, we know C equals the square root of 130, okay, we can find B because there's always that formula that relates the 3. Now just remember again, for the hyperbola, the C is the biggest one, right? The focal point are farther away from the center than the vertexes, so C is bigger than A. So this is the standard arrangement of the Pythagorean theorem. The C squared must equal to A squared plus B squared. Okay, so C is the square root of 130, so that squared must equal A squared, so 7 squared, plus B squared. Okay, now this isn't too bad. The square root of 130, when you square it, just becomes 130, right? It just makes the square root go away. Equals 49 plus B squared. We can subtract the 49 and get 81 equals b squared. Okay, so that's telling me that b must be 9. Okay, now let's think about what b measures, and then we can write this equation. B measures the distance to the other part of the box. So from the center, we need to go 9 units that way and 9 units that way to get the rest of the rectangle. Okay, to write our equation though, here's all we need to think about. This graph opens up and down, so the y term comes first. Okay, so it's going to be the y term first, like we said, y plus 1 squared over, now think about from the center to the vertex, that a value was 7, so we're going to have a 49 under the y term, okay, minus the x minus 6 squared. Okay, and that distance we found from the center to the x sides is 9, so 81 under there. And hyperbolas always equal 1. Okay, so that would be the, not 11, what did I write, 11? So that's the equation of this hyperbola. Okay, a little tricky on that one. But again, understanding that C is the distance to the focus, A and B are the length and width of the box. Okay, we can still kind of piece this together and use the Pythagorean theorem like formula there to put everything together. Okay.